Has this newly discovered planet vanished all of a sudden? Fomalhaut is one of the brightest stars in the sky, and it can be found in the constellation Piscis Austrinus, or the Southern Fish. According to the amazing Hipparcos expedition, it is a class of star, which means it is very hot and is located roughly 25 light-years away from the Sun. For a variety of reasons, Fomalhaut is a unique star. For instance, its gorgeous spectrum was utilized as a calibration spectrum for all the other stars, making it a reliable anchor point for star categorization. It is a Vega-like star that emits an excess of infrared radiation because it is encircled by the circumstellar disk. Fomalhaut is therefore fairly reddish as a result. Fomalhaut, commonly known as Alpha Piscis Austrini, is part of a triple star system that also includes the stars TW Piscis Austrini and LP 876-10. What, though, makes Fomalhaut even more unique? To learn more about it, stick with me in this video. Additionally, you will discover that science is not always clear-cut and that various interpretations of the same facts exist within the scientific community. In other words, scientists are people just like you and me, and the universe is complicated. In essence, NASA declared the discovery of an exoplanet in 2008. The discovery was made on November 13th by the Hubble Space Telescope. Since it was one of the first exoplanets to be directly observed, this discovery was highly significant historically. In a nutshell, we had a photo of it. Hubble, the well-known exoplanet hunter, among other things, was competent in his field. It clarified the Fomalhaut star structure in 2005 and discovered that the star was encircled by a sizable cold debris disk. The ring has a sharper inner edge and is not centered on the star. This enormous disk's presence aided in the search for exoplanets. In reality, we would have witnessed something extraordinary if this debris ring cloud contained a planet, perhaps a large one with a wide orbit. The ring would have seemed to have a sharp inner border and to be offset from the star, as we precisely observed, because this planet would have cleaned out parent bodies and dust in its vicinity. There was a planet discovered in May 2008. In the visible spectrum, Paul Cullis and James Graham from NASA discovered it in HST pictures from 2004 and 2006. In 2008, NASA made the composite discovery image public. Anyway, questions soon began to surface. Let's explain how HST detects exoplanets in order to comprehend what was going on. As the name implies, direct imaging is taking pictures of exoplanets directly, which is made possible by looking for infrared light that is reflected from a planet's atmosphere. This is due to the fact that a star is less likely to be a billion times brighter than a planet that is reflecting light at infrared wavelengths than it is at visible wavelengths, when it is usually the case. The fact that direct imaging is less likely to produce false positives is one of its most obvious benefits. Planets discovered using the radial velocity method need to be confirmed, which is why it is typically used in conjunction with the transit method. In contrast, the transit method is susceptible to false positives in up to 40% of cases involving a single planet system, demanding follow-up studies. Direct imaging, on the other hand, enables astronomers to actually view the planets they are looking for. Although there aren't many opportunities to use this technique, when they do, it can give researchers important insights on the planet. Astronomers can learn important details about a planet's composition, for instance, by analyzing the spectra that are reflected off its atmosphere. This knowledge is essential for characterizing exoplanets and evaluating if they may be habitable. This technique lets scientists determine the mass of Fomalhaut B, learn more about the planet's interactions with the star's protoplanetary disk, and confirm the existence of a huge ring system. In their study detailing the planet's discovery, Cullis and colleagues hypothesized that Fomalhaut B's emission comes from both thermal emission from the planet and circumplanetary dust scattering. Therefore, if its mass is between 1 to 3 Jupiter masses, it should be visible in space-based infrared data. Fomalhaut b, however, was undetectable by the sensitive infrared Spitzer Space Telescope measurements, suggesting that it has a mass less than 1 Jupiter. Furthermore, observations in the Cullis et al. Publication suggested that the planet was moving too quickly for this theory to be valid, despite the planet being considered a reasonable explanation for Fomalhaut's eccentric debris ring. As Cullis point out, despite their dissimilar ages, the primary Kuiper belt of our solar system and the debris ring of Fomalhaut are dynamically comparable. The traditional Kuiper belt has a very low forced eccentricity, whereas the Fomalhaut debris ring has a considerable forced eccentricity of roughly 0.1, which may be a significant difference. Such findings, particularly those suggested by ALMA, the Atacama Large Millimeter Array, raised doubts regarding the designation of Fomalhaut b as an extrasolar planet. Was HST detection a straightforward error then? Fomalhaut was suspected by astronomers to be a massive dust cloud. A group of astronomers claimed in a paper they released in 2021 that there was no Fomalhaut b planet. The observations taken with the Spitzer Space Telescope provided evidence for this investigation. You'll respond, closed story. But no, since a few months later, a third publication was released in which the authors gave Fomalhaut b the designation of exoplanet based on information collected from the Subaru telescope in Hawaii. In fact, a fourth research reverses course and claims that Fomalhaut b is not a planet at all, but rather a massive expanding cloud of particles, maybe the product of a cosmic collision. This study was released in 2020. Andres Gasper, an astronomer at the University of Arizona Steward Observatory and the study's first author, claims that our study, analyzing all the Hubble data available in the archive on Fomalhaut, revealed several characteristics that collectively paint an image according to which the planetary-sized object may have never existed. The author claims that there isn't a planet there, rather, it is a mixture of ice and dust made up of particles that are about 1 micron across, or about 1/50th the width of a human hair, and that were created by the titanic collision of two planetesimals that, by their estimates, were each about 200 kilometers across, or about half the size of the asteroid Vesta. As of right now, we can rely on predictions that are very accurate for the Fomalhaut system's increasing cloud. Such theories are based on our understanding of the solar system's Kuiper belt. The Kuiper belt is a region of debris from the early solar system's past, much like the asteroid belt is. It was also fashioned by a large planet, just like the asteroid belt, however it is more of a thick disk than a thin belt. Since we are only now starting to study it and comprehend it better, the Kuiper belt is genuinely a frontier in space. Regarding this dust cloud, I believe reading the abstract of this research piece, which is dated 2018 and has the astronomers Lawler, Greenstreet, and Gladden's signatures, would be very instructive. It needs a sizable, reflecting dust cloud to explain why the planet candidate Fomalhaut b is visible in optical light but invisible at longer wavelengths. Fomalhaut b cannot be the planet that is limiting the eccentric debris ring in the system because the most recent measurements reveal a highly eccentric orbit with an eccentricity of 0.8. However, explaining the well-constrained debris ring needs an additional planet with an orbit that overlaps the path of the hypothetical super-Earth. An irregular satellite swarm orbiting a super-Earth has been proposed. This essay develops a second theory. A cataclysmic collision between planetesimals in the disk gave rise to the transitory dust cloud known as Fomalhaut b, based on the structure of our Kuiper belt. We run collisional probability simulations of the Fomalhaut debris disk and discovered that the catastrophic disruption rate of bodies with a diameter of about 100 kilometers and the high eccentricity scattering component is several per decade. This hypothesis suggests that the Fomalhaut system suffered a dynamical instability within its planetary system within the last 10 to 100 million years, which dispersed a large number of planetesimals onto giant, high-eccentricity orbits similar to that of Fomalhaut b. We should soon observe another if Fomalhaut b is in fact a dust cloud created by such a collision, and Fomalhaut b will continue to grow until it either resolves or becomes too faint to be detected. The essay demonstrates that our Fomalhaut B as a dust cloud hypothesis makes two predictions. The first is that the Fomalhaut B expansion will eventually allow our telescopes to resolve the object, allowing us to view it more closely. The creation of other dust clouds similar to Fomalhaut B is expected to occur in the system soon, according to the second forecast. We could finally put a pin in it if one of these two possibilities is proven to be accurate. We must only wait and maintain our curiosity. Here's where the video ends. Thank you everybody for watching.